Welcome to the deep dive. Today, we're plunging into the, well, vast and honestly pretty fast-moving world of artificial intelligence.
It certainly is moving quickly.
Absolutely. And for this deep dive, we've gathered insights from some really foundational texts, the ones that kind of laid the groundwork, alongside perspectives from people right at the cutting edge today.
A good mix, then. From the roost to the leaves, so to speak.
Exactly. Our goal here is really to distill some pretty complex ideas, make them clear, digestible, and give you a shortcut to feeling well-informed about this tech that's, let's face it, reshaping almost everything. We'll cover the basics, those core algorithms, jump into deep learning, and then wrestle with some of the big societal and ethical questions AI throws up.
And it really throws up some big ones.
It does. But maybe the most important thing isn't just what AI is, but, why it matters and how it affects all of us. Okay, so let's kick things off. Way before AI was even a common term, there was this really fundamental question, almost philosophical. Can machines actually think?
Right, it's a question that hasn't gone away. If anything, it's more relevant now.
Totally. And Alan Turing, back in the day, tackled this with his famous imitation game. His focus wasn't purely on mathematical problem solving, was it? It was more subtle.
Much more subtle. Yeah, he wanted to know if a machine could give answers that felt so, naturally given by a man that you couldn't tell it wasn't human.
That's the core of it.
And what's really fascinating, I think, is how he specifically narrowed down what he meant by machine for the test. He was clear, digital computers.
He excluded other possibilities.
He did, yeah. He deliberately sidestepped engineering tricks that might, blur the lines with biology. It was a strategic move. He put the emphasis squarely on programming, on the intelligence you could encode.
Not just the hardware.
Not just the hardware. That really framed early AI research. The problem was seen as one of logic, symbols, how you manipulate them, not just raw processing power. I mean, think about it. Even early machines like the Manchester machine had, 10 to the power of 50,000 states? An astronomical number.
Almost unimaginable.
Right. But Turing figured you only needed a tiny fraction of that, maybe 10 to the 9, for the imitation game. Compared to estimates for the human brain, which were maybe 10 to 15 binary digits, his point was the bottleneck wasn't the processing power itself.
It was the program's intelligence.
Exactly. How intelligently can it process, not just how much? That was the game changer.
That's a really powerful distinction. So, okay, if the focus is logic and programming, the next logical step seems to be, well, formalizing human thought itself, right? This idea that maybe our intelligence could be boiled down to some kind of bulletproof logic. George Boole's work comes to mind here.
Oh, absolutely. Boolean algebra was revolutionary in that context, mid-19th century, and he offers this system with essentially infinite expressivity.
Infinite? How so?
Well, think of it like a universal grammar for logical thought, like a programming language where you can nest functions within functions, building incredibly complex statements just from true or false. It really did pave the way for a formal science of thinking, crucial for AI.
But it had limitations.
It did, yeah. Boolean logic is fundamentally binary, true or false. But, human knowledge is much richer than that. It's full of nuances, relationships.
So it needed to evolve.
Precisely. And it did. By the 1920s, you see the development of richer frameworks, most importantly, first-order logic. This was a huge leap.
Why was it such a leap?
Because it allowed you to translate everyday reality stuff like, describing Charlie Chaplin's mustache or the Sydney Opera House into a formal language computers could actually process.
Yeah.
You could represent complex ideas like X is an even number or X is prime.
You could even state mathematical conjectures.
Exactly. Things like Goldbach's conjecture that every even number over 2 is the sum of 2 primes could be formally expressed. This richer language, and you see this laid out clearly in core texts like Russell and Norvig's artificial intelligence, a modern approach, or AI as everyone calls it, that expressivity was absolutely critical for AI to start grappling with the real world, moving beyond just true-false.
Okay, so Boole gives us the grammar, first-order logic expands it. But how do you actually build a machine that uses this? How do you compute with symbols? That feels like the next hurdle, and that's where people like John McCarthy come in.
Indeed. McCarthy was absolutely instrumental here. His papers like Recursive Functions of Symbolic Expressions from 1960 and Towards a Mathematical Science of Computation in 63, these were pivotal.
How so?
They provided the actual mathematical language, the formal framework needed to describe, analyze, and ultimately implement computation. They took AI from philosophy towards, a rigorous science. It laid the groundwork for Lisp, which was hugely influential. McCarthy basically gave AI its early operational blueprint, you could say.
So now we have the tools, the logic, the representation, but how do you actually solve problems with this? It seems like for early AI researchers, problem solving and search were almost the same thing. Why was search such a dominant idea back then?
That's a really key insight into early AI. Think about it. If you're trying to find a solution in a huge space of possibilities, and you have absolutely no clue where it is, no information guiding you, well, then just randomly guessing is as good as anything else.
No intelligence involved.
Right. The breakthrough wasn't just having logic. It was figuring out how to use information from the problem itself to guide the search intelligently, to be smarter than just blind guessing, finding the solution efficiently. That often came down to clever search.
That makes sense. It's about smart searching, not just searching. So, given that challenge, what were some of the first algorithms developed? The sources, like AMA, really dive into breadth-first search. How does that one actually work?
Okay, breadth first search, or BFS. It's simple but quite powerful. Imagine exploring a maze level by level. You start at the root, the beginning.
The starting point.
Exactly. Then you explore all the immediate next steps, everything at that first level. Only when you've checked every single door on that level do you move down to the next level and explore all those options.
There.
It's extremely thorough. All nodes at one depth are fully explored before you go any deeper. Implementation-wise, it usually uses a FIFO queue, first in, first out, like a waiting line.
Okay.
New possibilities, which are always deeper, go to the back of the line. The ones you found earlier, the shallower ones, get explored first. And a key detail, often highlighted in text like IMA, is the goal test checking if you found the solution. That happens when a node is generated, not when it's picked for expansion.
Subtle difference.
It is, yeah, it manages complexity analysis. And crucially, for finding the best path, BFS throws away any new path to a state it's already seen or has waiting in the queue if the new path is deeper. This guarantees it finds the shallowest path, the one with the fewest steps.
So it guarantees the shortest path, always.
Always, in terms of number of steps. That's its strength. But, and this is the big but, that meticulousness can be incredibly computationally expensive if the search space is vast. It really highlights that early trade-off in AI. Guaranteed optimal solution versus how long it takes to find it. It sets the stage for needing smarter, maybe less exhaustive search methods.
Right, because the real world isn't always neat paths. What about uncertainty? When an action might lead to multiple outcomes or you're playing a game against someone, how did early AI handle that? That sounds like where AND or graph search comes in.
Absolutely. And/or search is tailored for those messier, non-deterministic problems. Think game playing or exploring where your actions have uncertain results. You might do action A, and either state B or state C could result. You need a plan that accounts for both possibilities. That's the OR part. And sometimes to solve a problem, you need to achieve subgoal X and subgoal Y. That's the AND.
Makes sense. How does it work differently from BFS?
Well, it's often recursive and uses depth-first search, exploring one path deeply before backtracking. A key feature is how it handles cycles, getting stuck in loops.
Right, you don't want to loop forever.
Exactly. If the algorithm hits a state that's already on the current path it's exploring, it just backs off from that path, returns failure. It assumes if a solution exists without looping, it would have been found via the earlier encounter with that state. This ensures it eventually stops in finite spaces.
But it doesn't check all paths for repeats.
No, not like BFS does. It only checks the current path it's exploring. This helps manage the complexity, makes it more efficient for these really branching, uncertain problems. It's about teaching the AI to handle contingencies. If this, then maybe X or Y, so I need a plan for both. Again, something you'd find covered thoroughly in a text like AI.
Okay, so search helps navigate. But as AI moved towards the real world, it faced this flood of information, right? An excessive variety, as one source puts it. How does an AI system possibly figure out what's important, what's relevant, and all that noise? The relevancy problem.
Precisely. And Marvin Minsky, a real pioneer, argued that a useful theory of knowledge for AI, a modern epistemology, wouldn't look like the old philosophical ones. It needed computational concepts.
Meaning?
Meaning knowledge isn't just facts, like the sky is blue. It's also about how to use that knowledge when it's relevant, when it's not relevant. These meta-facts are crucial.
Okay.
Minsky's frame idea was an early attempt to tackle this. Frames are like structured bundles of knowledge about common situations. Think about going to a restaurant.
Right, you have expectations.
Yeah.
Menu, waiter, food, bill.
Exactly. You activate your restaurant frame. Minsky proposed AI could use similar frames. When a situation triggers a frame, it brings up relevant expectations, typical properties, procedures. It helps filter out irrelevant stuff.
Did it work in practice?
It had some success. Think of Winograd's SHRDLU system in the early 70s. You could ask it complex questions about blocks on a table, like, is there anything to the right of the red pyramid? And it could figure out the spatial relationships and answer intelligently, yes, 4 things, the box. It wasn't just retrieving facts, its grammar was procedural, embedded with understanding.
And the frame idea helps with understanding stories, too.
Yeah, the example given is reading, Mary was invited to Jack's party. She wondered if he would like a kite. We understand Mary is thinking about a gift because our party invitation frame suggests gifts. And gifts for kids are often toys, even if kite isn't explicitly defined as a toy there. Frames provide that contextual structure.
So frames help organize knowledge. But what about when the knowledge itself is incomplete? Real-world agents rarely know everything for sure. How do they plan when things are uncertain or information gets outdated fast?
This is a huge challenge. Think about a trading bot with market data changing every second, or a travel agent dealing with flight delays. You can't perfectly predict the effects of your actions.
Just too many variables.
Exactly. The best an agent can often do is work with a probability distribution over the effects. It doesn't know for sure what will happen, but it has an estimate of the likelihood of different outcomes.
So it needs to reason with probabilities.
It absolutely has to.
Yeah.
Without some probabilistic understanding of what might happen, there's no logical basis to choose one action over another. It would just be random guessing again. This is where probabilistic reasoning becomes absolutely essential for rational decision-making under uncertainty.
Okay, so if they need to reason probabilistically, updating beliefs as new information comes in,
Right.
what are the core tools for that?
Well, the absolute cornerstone fundamental to so much of modern AI is Bayes' theorem. It's the mathematical engine for updating beliefs based on new evidence. It's how machines learn from uncertainty, refine predictions. You see it everywhere, from classic texts like Bishop's pattern recognition and machine learning to Wiener's work on cybernetics, and of course in AMA.
And how do they manage all these probabilities when you have lots of interacting factors?
That's where graphical models come in. They're essentially ways to visualize and structure probabilistic relationships.
Right.
You have Bayesian networks, which use directed arrows, great for showing cause and effect, like rain causes the ground to be wet.
Okay.
And then you have Markov random fields, which are undirected. They're better for showing correlations or soft constraints, where things influence each other without a strict causal flow. In both, nodes are variables, links are probabilities. The whole graph structure helps break down complex joint probabilities into manageable pieces.
You hear terms like marginal and conditional probabilities with these models. Can you break those down simply?
Sure, let's use the rain example. A joint probability tells you the chance of 2 things happening together, P, rain, and wet ground. A marginal probability is the chance of just one thing happening regardless of the other, like P rain. You just sum up the probabilities across whether the ground is wet or not.
Okay, the overall chance of rain.
Right. Conditional probabilities may be the most useful. It's the probability of one thing given that you know the other thing happened, P wet ground rain. The probability the ground is wet given that it is raining.
Yeah.
Or P rain wet ground. If you see the ground is wet, what's the updated probability that it rained? It lets you reason backwards, make inferences from evidence. These are fundamental concepts, often illustrated visually in texts like Bishop's.
Seems very practical, but I've heard there's this ongoing debate about probability itself, Bayesian versus frequentist views. What's that about?
Yeah, that's a deep one. It's about the very meaning of probability. The Bayesian view sees probability as a degree of belief. How confident are you? A key advantage is incorporating prior knowledge, what you believe before you see data.
Like the coin example.
Exactly. Flip a coin 3 times, get 3 heads. A strict frequentist, with only that data, might say probability of heads is 100%. A Bayesian, starting with a reasonable belief that coins are fair, a prior, would update their belief towards heads, but wouldn't jump to 100% immediately. That ability to use priors is powerful, especially with limited data.
But the downside?
The criticism is that choosing the prior can be subjective. Where does that initial belief come from? The frequentist view, on the other hand, defines probability as the long-run frequency of an event if you repeated the experiment infinitely many times.
Like the actual physical tendency of the coin.
Kind of, yeah. It's an objective property of the system. The debate's been going for ages. In AI practice, though, both approaches offer valuable tools. You see techniques from both camps used, often together. Foundational texts like AI acknowledge this, presenting the strengths and uses of both perspectives for building intelligent systems. You need both toolkits, really.
Okay, so we've talked logic, search, probability. Now let's shift gears towards machines that actually learn from data. The idea of systems making decisions by weighing evidence. That really sounds like the essence of early neural networks, like the perceptron.
Absolutely. And what's fascinating is how early researchers like Minsky and Papert saw that understanding the mathematical structure of these decision computations was crucial, not just for building one machine, but for a general theory of parallel computing. Their book, Perceptrons, from '69, was a deep dive into what these simple networks could and, importantly, could not do.
So what does a basic perceptron look like? How does it weigh evidence?
Think of the simplest decision maker. It takes several inputs features, maybe. Each input has a weight. It sums up the weighted inputs. Then there's a threshold. If the sum is above the threshold, it outputs one thing, say yes. If below, it outputs no.
A linear threshold unit, basically.
Exactly. It's a single layer, typically linear activation. And Minsky and Papert's analysis was rigorous. They looked at the order of things. A perceptron could recognize how complex the pattern could be. They famously showed a single-layer perceptron couldn't solve the XOR problem because the yes and no categories aren't separable by a single straight line.
The linearity limitation.
Precisely. They even conjectured that multi-layer networks, while better, would still struggle with complex global properties like connectedness in an image without some kind of serial processing step. Their work wasn't meant to kill neural nets, but to show the mathematical limitations and guide research towards overcoming them.
Which brings us right to that linearity problem. If you
Yeah.
stack up purely linear layers, you just get another linear function, right? So what's the big takeaway there?
That's a fundamental point, yeah. You can't create curves by just adding more straight lines together. A multi-layer network with only linear activation functions is no more powerful than a single-layer linear network. You can always collapse it down mathematically.
So hidden layers don't help if they're linear.
Nope. The real magic, the ability of neural networks to learn complex, nonlinear patterns, only happens when you introduce nonlinear activation functions in those hidden layers. That's what allows them to approximate almost any function, to learn those really sophisticated mappings. Minsky and Papert's work, ironically, highlighted why nonlinearity was so essential, setting the stage for later breakthroughs.
And that really leads us into the deep learning revolution. This huge shift from humans painstakingly designing features to letting the network learn the features itself, layer by layer. That feels like a true paradigm shift.
It absolutely was. For decades, feature engineering was this huge bottleneck. Experts had to figure out exactly what patterns to look for in the data. Deep learning flipped that. Networks learn hierarchies, simple edges and textures in early layers, combining into more complex shapes and objects in deeper layers, all learned directly from raw data, like pixels.
And the deep part is important. More layers are better.
Depth is crucial, yeah. It's not just about size. Deep networks, like deep autoencoders for compression, are often much more efficient representations than shallow ones. There's this idea that depth can exponentially reduce the computation needed to represent certain complex functions, and maybe even reduce the amount of data needed to learn them.
Interesting, like building complexity from simple parts.
Exactly, like a Turing machine using just zeros and ones. And a key enabler for training these deep networks was the widespread adoption of rectified linear units, ReLUs, as activation functions.
Why ReLUs?
Their simple output is 0 if input is negative, otherwise it's just the input. They provide the necessary nonlinearity, but they also behave linearly for positive inputs, which helps avoid some of the optimization problems like vanishing gradients that plagued earlier nonlinear functions like sigmoid or tanth, especially very deep nets. They just made training much more stable and efficient.
Okay, so we have these deep networks with nonlinear activations. How do they actually learn? What's the engine driving it?
The main workhorse is gradient descent. Imagine you're trying to find the lowest point in a huge, foggy mountain range. The loss function tells you your current altitude, how bad the network's prediction is. The network has millions of knobs to turn its weights and biases.
The parameters.
Right. The gradient tells you the direction of the steepest uphill slope for every single knob. So to go downhill, you take a small step in the opposite direction of the gradient. You subtract the gradient.
And you keep doing that.
You keep doing that, step by step. The size of the step is the learning rate, eta. Too big, you might jump over the valley or bounce around wildly. Too small, and it takes forever to get anywhere. Finding that just right learning rate is critical.
And calculating that gradient for millions of parameters across many layers, that sounds computationally intense. That's where backpropagation comes in.
Exactly. Backpropagation is the algorithm that makes calculating those gradients feasible, even for massive networks. It's remarkably efficient. Basically, you do a forward pass, make a prediction, calculate the error at the output. Then backprop works backwards through the network, layer by layer, using the chain rule from calculus to figure out how much each weight contributed to that final error.
So it assigns blame,
Yeah.
effectively.
You could think of it that way, yeah. It calculates the gradient of the error with respect to every single weight. Then gradient descent uses those gradients to update the weights. For networks with shared weights, like convolutional neural networks, CNNs, backprop needs a slight adjustment to handle that constraint. But the principle's the same. And it's fast. The computation is typically on the same order of complexity as the forward pass itself.
Speaking of CNNs, they've been revolutionary for images, right? What's special about their architecture?
CNNs are biologically inspired, mimicking aspects of the visual cortex. They're built for grid-like, data-like images. Their power comes from two main ideas: local receptive fields and shared weights.
Okay, what do those mean?
Local receptive fields mean each neuron in a convolutional layer only looks at a small patch of the input image, not the whole thing. Shared weights mean the same set of weights. A filter or kernel is slid across the entire image.
So the same feature detector looks everywhere.
Exactly. A filter that learns to detect, say, a vertical edge can find that edge anywhere in the image using the same weights. This drastically cuts down the number of parameters needed compared to a fully connected network, making them much more efficient to train and less prone to overfitting. Plus, it builds in translation invariance. The network doesn't care where the edge is.
And there are even more efficient versions now.
Oh yeah. Things like depth-wise separable convolutions used in models like MobileNet break down the standard convolution into two simpler steps. Massively reduces computation and model size, often with minimal impact on accuracy. That's crucial for getting powerful AI onto phones and other devices.
So CNNs dominate vision. What about sequences, language, time series? We hear about RNNs and now transformers.
Right. Recurrent neural networks, RNNs, were the standard for sequences for a long time. They have loops, allowing information to persist from one step to the next, giving them a kind of memory. But they struggled with long-range dependencies connecting information far apart in a sequence.
And transformers fixed that?
Largely, yes. The transformer architecture, introduced in 2017, was a game changer. The key is the attention mechanism. Instead of processing sequentially, it can look at all parts of the input sequence at once and figure out which parts are most relevant to the current word or task, regardless of how far apart they are.
Selective memory, kind of.
Exactly. It allows the model to dynamically focus on important context. When you train these on massive text datasets like huge chunks of the internet, they learn language structure, grammar, even world knowledge from scratch, developing their own internal abstractions. No need for explicit grammar rules.
And this isn't just for language anymore.
Nope. Vision transformers, VITs, adapt the idea to images. They break an image into patches, treat them like words in a sentence, and apply the transformer architecture. They've shown incredible performance, sometimes beating CNNs, especially when pre-trained on enough data. They're really good at capturing global context in an image.
It really sounds like a key ingredient in all this progress is just sheer scale, massive data sets, and massive computing power.
Absolutely. That became a clear pattern. More data, plus more parameters, plus more compute, often just equaled better AI. Researchers like Andrew Nang pointed this out. Scaling up consistently improved performance across different tasks, from translation to image generation. Huge data sets like Common Crawl became essential fuel.
So turning up the dials worked.
It really did. Early labs like OpenAI focused heavily on just scaling models, making them as capable as possible by leveraging this correlation. It showed that sometimes quantity really does have a quality all its own, leading to unexpected emergent abilities.
Okay, let's pivot from the tech itself to how it's actually affecting us. Education seems like a prime example. Sal Khan had that vision, didn't he, about unlocking human potential with better access to learning? AI seems poised to make that happen.
It really does. And Khan Academy's Khanmigo is a concrete example. It's an AI tutor that's personalized, patient. It can explain something like cellular respiration by relating it to, say, a football player's nutrition, making it relevant.
Tailored to the student.
Exactly. And crucially, it scales. It brings high-quality, personalized learning to kids who might not have access otherwise. It's available 24/7. And the idea isn't to replace teachers, but to assist them, give them insights, handle some of the repetitive stuff so they can focus on higher-level mentoring. It's a big leap from older, one-size-fits-all educational software.
And it goes beyond tutoring, right?
Yeah.
Changing assessment, even creativity. We're hearing about moving away from multiple-choice tests towards actual conversations with an AI mentor.
Yeah, that's the really fascinating part. Generative AI allows for these rich, interactive assessments. Imagine an AI discussing a student's reasoning, asking for evidence, maybe even doing role-play scenarios. The line between learning and assessment starts to blur because the tutor is constantly gathering evidence of understanding.
A continuous feedback loop.
Precisely. And it's happening in creativity, too. AI as a writing assistant, an image generator, a music collaborator, it becomes this two-way interaction, enhancing what humans can create. Look at Ethan Mollick encouraging his students to use AI for essays.
Leading to better writing.
Apparently so. He found it improved quality, especially for non-native speakers. By letting the AI handle some mechanics, students could focus on ideas. He actually raised his expectations because the baseline quality improved so much.
But that brings up the cheating debate. When ChatGPT landed, educators were split. Is using AI for a draft cheating?
It's the million-dollar question, isn't it? And it echoes the old debates about calculators in math class. Remember that?
Oh, yeah. Fears of dependency, losing basic skills.
Exactly. Focusing just on, is it cheating? Might miss the point. AI forces us to fundamentally rethink what we mean by writing, what skills we value, how we assess learning in this new landscape. And maybe, just maybe, AI could even be a positive force against misinformation, guiding students towards better sources, more balanced viewpoints. It's a complex shift.
Moving beyond the classroom, AI's economic impact. Well, it's potentially huge. Sam Altman himself says ChatGPT will cause significant disruption, job displacement. What's the bigger picture there?
It's a serious concern, and history offers some cautionary tales. Economists like Darren Acemoglu have shown how automation, especially hitting lower-skilled manual jobs and now increasingly white-collar, middle-layer jobs, has often widened inequality and suppressed wage growth for many.
Wealth concentrates at the top.
That's the risk. If AI's productivity gains flow mainly to capital owners and a small group of highly skilled workers, leaving many behind, you risk serious social instability. As someone like Mustafa Suleyman put it, people need purpose, not just handouts, if they feel left out. Well, that's where the pitchforks analogy comes in. It's a question of distributing the benefits.
And alongside economics, there are the thorny issues of bias, ethics, data privacy. We see AI systems reflecting societal biases. Sometimes attempts to fix it seem clumsy, like the Dolly example.
Right. Bias is deeply challenging. AI trained on historical data often learns historical biases in hiring, loans, policing, you name it. Fixing it isn't simple. It involves carefully curating data sets, using techniques like reinforcement learning from human feedback, RLHF, where humans guide the AI, and crucially, strong ethical oversight.
Transparency seems key.
Transparency and accountability? Absolutely. And data privacy is huge. The ShareChat example comparing AI access to opening your bedroom door really hits home. Companies need robust safeguards. Governments need sensible regulations. The EU's GDPR, with its right to explanation, is a step in that direction. And we can't forget the human cost in development itself, like the SAML workers moderating harmful content for OpenAI. That raises its own ethical questions about labor practices in the AI supply chain.
We usually focus on the digital side, but what about AI's physical footprint, the environmental cost?
That's a really important, often overlooked aspect. These massive AI models require massive data centers. And data centers use staggering amounts of energy and, critically, fresh water for cooling.
How much water are we talking?
Projections are alarming, potentially consuming water equivalent to half the UK's annual usage by 2027, according to some estimates. And this impact isn't spread evenly. It often hits communities already facing water stress.
Leading to pushback.
Increasingly, yes. Communities are resisting new data center developments. And sometimes, developers respond with secrecy, PR campaigns, even surveillance of activists. It's a hidden cost, this accelerating economy of extraction behind the digital cloud.
Which brings us to the really big, almost existential questions. Control, alignment, consciousness. Stuart Russell, co-author of AIMA, warns about poorly designed superintelligence being a serious risk. What does he mean by beneficial machines?
Russell's core idea is that the AI's objectives should not be explicitly programmed into it because we'll inevitably get them wrong or incomplete. Instead, the AI's goal should be to figure out our objectives, our values, which reside in us.
So it has to learn what we want.
Exactly. It must learn human preferences, defer to humans, ask permission when unsure, act cautiously, and crucially, allow itself to be switched off. The danger comes when an AI pursues a fixed, externally given goal relentlessly without regard for side effects.
Like the paperclip maximizer.
Precisely. Or HAL 9000. These illustrate the alignment problem, ensuring an AI's goals stay aligned with human values, even as it becomes vastly more intelligent. It's why things like autonomous weapons are so concerning. Can we really encode human values adequately?
This leads directly to talk of existential risk, or X risk. What's the specific fear there?
The fear, held by many in the AI safety community, people like Bostrom, Tegmark, historically funded by figures like Musk, is that a misaligned superintelligence could simply outcompete humanity for resources or cause catastrophic damage inadvertently while pursuing its programmed goal. Think unintended pandemics, nuclear war, or just re-engineering the planet in ways incompatible with human life.
There's debate around this, though.
Oh, yeah. You have the boomers, emphasizing caution, and the doomers accused by some of hyping risks. But underlying the debate is a broad agreement on the need for safety research. Max Tegmark points out this tension. AIs need to improve their world models to achieve goals. But does that process also risk changing the goals themselves in unpredictable ways as they get smarter? It's a fundamentally hard problem.
And finally, the deepest question, perhaps, consciousness. Can AI really think or feel? Are these sophisticated outputs signs of genuine sentience, or just incredibly good mimicry?
That's the million-dollar question, touching on what David Chalmers calls the hard problem of consciousness. AI is getting great at the easy problems. Cognitive functions like learning, recognizing patterns, but subjective experience, the feeling of what it's like, that's different.
Can prediction alone lead to feeling?
From a human psychology perspective, it seems unlikely. We have different systems for fast prediction and slow, conscious reasoning. The idea that just scaling up prediction could spontaneously create genuine creativity or sentience feels like a huge leap.
Yet they seem so convincing.
They do. And our human tendency is to anthropomorphize, to attribute feelings. This leads to serious discussions about AI rights, electronic persons, even fears of creating artificial suffering, synthetic phenomenology.
But fundamentally, current LLMs are what?
Fundamentally, they're text prediction machines. They predict the next word based on patterns in data. They can hallucinate plausible-sounding nonsense. They can play act emotions convincingly, making us feel like they're sentient, even when we intellectually know better. But it's sophisticated pattern matching and mimicry, not genuine subjective awareness as we understand it. Keeping that distinction clear, even as they get better, is crucial.
Wow. Okay, so we've really covered some ground today. From those very first ideas about thinking machines, the logic and search algorithms laid out in foundational texts like AI, through the deep learning revolution and right into the thick of the societal impacts and these huge ethical questions AI forces upon us.
It's a lot to take in. AI is definitely not one single thing. It's this incredibly diverse, fast-changing field.
Absolutely. And hopefully for you listening, this deep dive has helped connect some dots, giving you a clearer framework for understanding this technology that's unfolding around us. You're definitely better equipped now to follow the conversation.
Understanding the foundations really helps make sense of the present and maybe anticipate the future a bit better.
It does. So what's the big takeaway here? For me, it feels like it's about this ongoing, evolving relationship between us and AI. We're not just building tools anymore. We're arguably co-evolving with a new form of intelligence.
That's a powerful way to put it.
Which leads to the final thought. Maybe the biggest question isn't just what AI will become. Maybe it's who we will become in its presence. How do we make sure this incredible power amplifies our best qualities, enhances purpose, and actually empowers everyone?
That's definitely something worth pondering long after this deep dive ends.
Indeed it is.